Hey, hello, workshop students. All right, let's try one from our energy chapters here. I got a question about the roller coaster here on this vertical loop. So I'm going to read it here. It says a frictionless roller coaster with a mass of 126 kilograms starts from rest at a height of 24.2 meters above the ground. And so I'm just going to draw the picture next to here I am reading. It rolls onto a vertical loop with a radius of 7.16 meters, whose lowest point is then touching the ground. The normal force on the roller coaster from the track at its highest point of the loop is then NT. Now, they give you a free body diagram that shows the weight pulling down mg. They also show a normal force pointing down as it comes and goes in a direction v. So they got a little blue color here for the velocity vector as it comes around, and it's upside down at this point. And they're saying that the normal force is down, and it probably is, but one thing about a roller coaster is, unlike a car, if this was a car going around, the road could only push it, perpendicular to the surface, down. The wheels can't hug a road. But on a roller coaster, that's not true. On a roller coaster, the wheels can hug. So the track on a roller coaster could go up or down. But anyways, they show it down. It probably is down. That's the most common process here. So let's see if we can find it before we get to part 2 of this. And here's the thing that I find useful. Since this is the first video I'm doing with energy, I like to make 2 columns and say the energy initial equals energy final. Okay? And that's the principle of conservation of energy. And I find that the 2 columns kind of useful. So I could look at maybe, say, here up at the top, because when I look at the top, I'd say, okay, well, what energies do we have? And so keep in mind, for your class right now, we really only have kinetic energy, gravitational potential energy, elastic potential energy, that's of a spring, and then the heat energy. As we go along, we'll find there's things like electrical energy and magnetic energy and nuclear energy and solar energy and sound energy, and the list begins to grow. But in terms of conservation of energy, we really could just, for this case, say, okay, there would be some kind of kinetic energy. Let me call it initial. There would be then some potential energy. Let me call it initial. If there was a spring involved, I might have an initial spring energy. There's no springs here, so I'm not even going to write that down. And then where does that go? Well, it all goes to, and then at the end, there could be some kinetic energy. So it looks like it's still moving, so it's going to have some kinetic energy. It could be at a height, so it could have some final potential energy, and it looks like it's going to have that. If there was a spring, it could have some elastic energy I would put here, but for this problem, no spring involved. And then if there's rubbing going on, there could be some heat. But it did say frictionless. Okay, so I'll cross that out. So there's no heat and there's no springs to worry about in this one. There's just the 2 types, the 2 easy types, the kinetic and the potential. So let's go to the beginning. The beginning says what does it say here? Frictionless roller coaster starts from rest. So kinetic energy, maybe I'll put it up here, is 1/2 mv squared, whereas potential energy is mgy or mgh. So when they start this problem by saying the roller coaster starts up here at 0 speed, they're really indirectly telling us that the initial kinetic energy is 0. And then, of course, the potential energy depends on where you put your y-axis. And I'm just going to put it at the ground. I will point out that you have that freedom of choice. I said that a lot when you were doing the projectile motions about picking the origin, picking which way is positive and which way is negative. You have that freedom of choice, so make it, but you got to stick to it for the rest of the problem. So you have that freedom of choice, but once chosen, it has power over you. So you got to stick to it. All right, so that's what I'm going to do. I'm going to pick the ground here because that makes this really nice. That means this roller coaster is a height of 24.2 because they say above the ground, and if I call the ground 0, then it makes it kind of easy. So this would be then mg, and I'll just say y initial. When I go to put in numbers here, I guess that would be 126 kilograms. G would be 9.8 meters per second squared. And the height would be 24.2 meters. Okay. And I was tempted to grab my calculator, but I'll calculate that in a second. Let's go to the left-hand side of the equation, because now the roller coaster comes down and goes around, and it's up here at the top of the loop. Okay, is that how they say it? It touches the bottom, the normal force from the... Yeah, is at the highest point. So at the highest point, it's going to have some kinetic energy. So let me just write it as 1/2 mv final squared. And I don't really know what that final speed is. I do know the mass. That doesn't change. That's going to be the 126. But I don't know that number. And then I have this gravitational potential energy, which is this mgy final. So how high is it now? And well, clearly it's the diameter of the circle, which is 2 radii. So I know that one. So let me put in what I do know here. And so this is a 1/2. The mass is the 126 kilograms. The final speed squared, I don't know. The mass, again, is the 126. The g is the 9.8. And the final height would be 2 times the 7.16 meters for the radius. Now, I guess I should have put my units. This is a kilogram. This is a meter per second squared. This is a meter. These first two make a Newton. A Newton times a meter is a joule, and so there's my units of joules. Same thing here, kilogram meters per second squared, that's a Newton, times that makes it a joule. And this would come out to be, if this is in kilograms and this is meters per second, joules also. So that's good. All of our units are in joules. That is the appropriate unit for energy. So over here, if I do the 126 times the 9.8 times the 24.2, and I subtract off, which would be this one, 126 times 9.8 times 2 times 7.16. That would be this one that's left over. So if I bring the 2 over, so multiply by 2, then divide by the 126, that would be the velocity squared. So then if I take the square root of that, I can come to the conclusion that the speed here at the top is 13.9 meters per second. Now, that's dandy, but it didn't really answer the question of what the normal force is. In fact, none of this energy even dealt with the normal force. I just jumped right in it because this was a chapter on energy. I probably should have given you a reason why we would want to do energy, and you would see that when you did the forces. Now, we're going to have to go back to chapter 6 here, where we learn the sum of all the forces equals ma. This is Newton's second law. And if we do a free body diagram, and so here's the roller coaster, one force is the force of gravity, and the other force is the normal. Each of those are pointing down, and that is towards the center of the circle. And if you remember our Chapter 6 stuff on circular motion, it says if you add up all the forces, okay, so in this case, N and mg, so I add them all up, which, by the way, notice I just called down positive by doing that, so I'm going to go with non-convention and call down positive. I'll even call it the x-axis. There's another non-conventional. So this is really the sum of the forces in the x direction, and that's going to give me mass times the acceleration in the x direction. And that's where we come back to chapter 6. We know that the acceleration towards the center of the circle is v squared over r, and these two are going down towards the center of the circle. So taking the center of the circle to be the x direction, that would mean that the two forces in the x direction, normal force and gravity, are here, and then they would be equaling to an acceleration, which we know because that's towards the center of the circle, and so that's v squared over r. So the normal force would be mv squared over r minus mg. And had I done this first, you would see then why I need to find speed. So I can put it here. And the way I did it perhaps was a little too quickly by jumping into the energy, just because I knew this was a chapter on energy. So I wanted to see where it would get me. But more than that, I wanted to show you about how I would lay out a problem with conservation of energy. I haven't done that. We've done a number of these, and you're hopefully starting to get pretty good at these, but haven't really done those. Anyways, this problem, and I can see why I'm getting a question on it now, really is new stuff and old stuff. And so we've got to put together our energy with our Newton's laws. Okay, so now I can hopefully do this and put in the mass, 126 kilograms. I'll put in the speed of 13.9 meters per second squared, divided by a radius of 7.16 meters, and subtract off the mass of 126 kilograms times g, which is 9.8 meters per second squared. And let's then see what you get here. And so here is the 126 times the last answer squared, then divided by 7.16, 7.16, then subtract the 126 times 9.8, and getting a normal force of 2,173 newtons. Maybe paying a little bit more attention to significant figures, 2,170 newtons then is what I would get for A. Okay. All right. Well, if I did that one correctly, well, I can move on to B. But B looks like it's going to be the same two principles. I got to use the energy, but I think I've also got to do normal forces here. Because this is where it says, and so here's what the second part says. It says, if the roller coaster is released from a height lower than h minimum, it will not have enough speed to make it around the loop. This occurs because the gravitational force is stronger than what is needed to provide the centripetal acceleration. The extra gravity, and quote, air quote, I'll do air quotes, but the extra gravity pulls on the roller coaster. All right, now, this fits with something that I've been saying. Step one in every problem is to get a good physical picture of what's happening here. Because if you don't see the fundamental physics of what's going on, you're not really sure what to do with this problem. Let me come back to the original picture. You see, if you were to lower the starting point of this roller coaster as it goes around and it got to the top, its speed would be less. And as its speed gets less, you can see over here that there'd be less of a normal force. And if a roller coaster is built like, I'll call it an older roller coaster, or maybe like a car, the normal force pushing down is all it can do. If you get so slow that you would need a force lifting you up to make it around. In other words, you would get right here and fall off and crash. And you wouldn't make it around the loop unless you had the capability of lifting upward, and so unless the wheels can hug the track. And many of your roller coasters these days do that, so there is no danger of it falling off. It's a little safer. But I think this is kind of going with kind of an old school roller coaster, or maybe a stunt driver in a car, where you got too slow, you get right here, you're going to fall off. You want to make sure you're going fast enough. And the one we just did, we went, so fast that there was, quite a bit of force tugging down on us. And the reason that is so important here is because the key here is now to realize here that the place where you would quote unquote fall off the track, or the minimum height, and that's what they're asking for, would when the normal force goes all the way down to 0. You see, you don't have to be at this high height of 24.2 meters, because you get around and you've got lots of normal force pushing you down. You could go a little bit slower than that, which would make the normal force a little bit less and a little bit less and a little bit less. But when the normal force gets to 0, anything slower than that means you either got to be pulling up and your normal force has to be negative, or you're going to leave the track. You're not going to make it around without falling off the track. In fact, I've always wondered if kind of a fun but scary ride would be the one where they actually let it fall off the track just momentarily. So you come up here whoosh, and you fall off the track, and then you catch the track. And so there's a separation between the cart and the track. You leave and regain. Obviously, could be really dangerous. But that's the kind of thing you see in the stunt movies. A car jumps off of a ramp and then lands on a ramp. This one's just kind of upside down. So anyway, it's probably a bit too scary for even a Magic Mountain ride here. But that's back to the problem. Where they're going to be talking about here the normal force. So again, without a good physical picture on this one, I'm not sure you know where to proceed. I'm not sure you would know where to translate your idea into math. And so that's the key. The normal force is 0. So if we go back to what we did earlier and set the normal force equal to 0 right here, and move the mg to the other side, you're saying mg would be equal to mv squared over r at that point. And then we could cancel off the m's, and we could even then solve for v, or even v squared. As you can see, it turns out that we really didn't need to get all the way down to v. Here we got v squared, and here we need v squared. So we never really needed to find v. But I'll find v just a little more out of curiosity. So square root. Okay, so what they're saying here is at the top of this roller coaster, there is a minimum speed, and it's not 0. See, that's why I wanted to emphasize just to make it to the top, you got to have a normal force of 0. That doesn't mean your speed is 0. That's what I'm trying to point out here in this physical picture. You go around this, you're going to leave the track before you get to the top. Whereas mistakenly, you could read this problem if you always assumed it was the roller coaster was attached to the track, that it could just slow down, and then barely make it so its speed is 0 at the top. That would be just barely making it. But it can only do that if it had some way to hang on, if it had some way to have a normal force lifting up, if it was somehow hugging the track. So I would agree that the slowest speed would be 0 if this was more of the type of roller coaster that wraps its wheels around and it can hug it, okay? But I don't think that's the gist of this problem. This is a roller coaster that could fall off if it's not going fast enough. So what is that minimum speed? It is not 0. It is, let's calculate it here. So it would be the 9.8 times the 7.16 and the square roots of all of that. So it looks like 8.38 meters per second is the slowest it can go. And like I said back in part 1 then, yeah, we were going a lot faster than that. So we easily made it around here. There was no danger in coming off. And again, that's kind of typical of, you know, how these roller coasters are made. You can feel it when you're on the roller coaster. They kind of slam you up. You're in no danger of falling out, even if your seatbelt came loose. And it's usually a seatbelt and a safety harness. You don't come loose. Now, some roller coasters, like Magic Mountain, you know, they will require a normal force going up. And some of those rides, you can feel it on your shoulder that if you didn't have that safety harness on, you would be thrown out the bottom. But the older ones, like the Revolution one, you know, you go down there and you go around the loop. Even if the seatbelt wasn't on here, you're just not coming out. You can just kind of still feel you're thrown in there. So it looks scary and you think it's scary, but once you're in it, you're like, oh man, I wasn't going to fall out. No way. All right, so finishing up this problem then, now we can get back to the energy. And so I would encourage you to say initial energy is equal to final energy. And in this case, when we are at the top of the hill, we would have a kinetic and a potential. And so we would have a 1/2 mv final squared and an mgy final. And then, of course, on the other side where we started, we would have the same thing as before. We would have some initial energy. And if we're starting from rest, so minimum height, starting from rest, we know the kinetic energy would be 0, so we don't need to include that. And we would just have over here mgy initial. And now we can put in our numbers, although we could also save ourselves a little bit before we put in the number by noticing the mass would cancel off. And we could also put it in because we know that number. So whatever you know you're happy with. I might even do this. I might even move this one over to here and factor out a g. So this becomes g. No, I'm sorry. We're trying to find for y initial, how high it is. I might divide by g. So maybe I'll bring the g over. So on this side, I would get v final squared over 2g. And then plus, and the g's would cancel off, the final height, which is the diameter, would equal the initial. Okay, so now I can put in my numbers. And in fact, as you can see, that number for the final speed is still in my calculator, so I'll just hit square, divide it by a 2, and also divide it by a 9.8. Add to that the final height, and as we said back in part 1, the final height is twice the radius, that is the diameter. So 2 times 7.16. And I get a minimum height, or a starting height, the way I put it. Starting height of 17.9 would give me just enough speed, this speed here, that would be just enough speed that the normal force would be 0, and that it would make it around the loop. All right, hopefully that was helpful.